now about the choice of what is called, so how we decouple, and this is called decoupling channel. So what we used above when we did the Hubbard-Sartonovich decoupling like a general way, we used some composite object which was called rho, and which corresponded to C bar A, C B, which meant that the interaction, which was potential delta C bar alpha C beta C delta, was written such that this coupled to rho alpha beta, rho gamma delta. So that was one specific choice that we did, and we noticed that well, we could have equally chosen two other combinations, which would be introduce some rho alpha delta, corresponding to psi bar alpha C delta. Then the interaction would have been one way alpha beta gamma delta. Now if we bring the two that we want to express through one operator, delta gamma C beta, so we had to put this here and that's this here. So in case of fermions, we would have required here sign, not for fermions, because for rearranging these fields, we would have had to use an odd number of permutations. So this would be for fermions. So the second choice would have been this way, alpha delta, and then there is a third choice. I'll just try to keep someone will tell it all. Part is we could have introduced some composite object corresponding to two creation operators, but then we should also give this some bar here, recalling that these are now two creation operators. Then the interaction term, if we rearrange expressions, again there could have been a one, there would have been a one, there would be a one if we consider fermions, alpha, beta, gamma, delta, and then bringing those two to each other would be C bar alpha, C bar gamma, was it gamma, alpha, beta, gamma, and C beta, C delta. So we would have paired this in this way. Now this would be a rho bar and this would be a rho. Okay? Just to differentiate here, this would be rho bar, rho. So this rho bar, rho, and this would be rho, rho, just to find a different way. Okay, so this is like the three ways we could, starting out from the interactions, could have done it. This is way number one, that we actually did it. We could have done it in another way, pairing the creation and annihilation. In the third way, we could have just paired two creation and two annihilations. Then the object here should tell us if there's the twos are creation or annihilation, so that's why we introduce rho bar. Okay? And these three ways actually also have names. So these are what is called the three different channels you can decouple your interactions. So this is called the direct channel, or also the density channel, but let's call it here first direct channel. And maybe the meaning becomes more clear once we discuss it in more detail. So this is a direct channel. This is called the exchange channel. And this here is called the Cooper channel. And the wordings, I think, once we come to the Coulomb interactions, it's clear more or less where these names come from. Once we discuss the example of commutation. Okay, so we find in general, if we do this prescription of the Hubbard-Sarton transformation, there's 3 ways to do it. We have chosen the one, but we've equally done it in the different ways. Let's recall like the ways are called channels, and there's 3 different names: direct, exchange, and Cooper. So let me just restate what I just said in some more diagrammatic way. That is, we have 3 channels in which we can do the decoupling. So we have 3 channels, let's say, available for the decoupling. And somewhat instructive to draw this in some pictures. So let's draw a general interaction vortex where we create an alpha and we create a gamma and destroy the beta, destroy the delta. Okay, so this would be convention how we could just represent the interaction diagrammatically. The delta, C bar alpha, C beta, C gamma, delta, the gamma. Okay, so just diagrammatic representation where this would be the interaction line, gamma, delta. Okay, so now let's draw this 3 times. Alpha, beta, delta, gamma. So let's draw it 3 times and let's see what these channels mean. It means that in a way what we put into a unit rho in the direct channel case would be this. So this would what we call rho. This would be the pairing how we do it in the direct channel. Let's just write direct, like direct channel, okay? Pairing it this way. This is in a way, if you think about it, like in the Coulomb interaction problem, I'm going to come back to this, this would correspond to like a state P scattering into P plus Q with the same spin, and this P prime minus Q scattering into P prime also with the same spin. So this would correspond to something like a density. So that's just a direct way that an electron with a certain spin scatters into another momentum state. So it's like a direct way. Okay? Now the other way that we said we could have paired instead of the incoming and outgoing in the direct way, we could have paired them like this. So this would evolve states if alpha and beta and so on would be states, momentum and spin. This would be with different spins. And if you think about it, what this means quantum mechanically, this just says, well, particles are indistinguishable, so there's always 2 scattering processes, no? Like if you think about quantum mechanics, there's a direct process, like if you could say one electron scatters from the other, well, that would be just the direct scattering, electron scattering from the other. But then, because they're indistinguishable, you cannot really say like which one is scattering like into the one state or the other, so there's always an exchange contribution. So this would correspond to the exchange process. And that's why it's called the exchange diagram. Now this involves all scattering of putting into some elementary unit, let's say creation and annihilation operator, some kind of density. Okay. But then we said there's also a third way. Well, we could introduce some rho and the rho bar, which would correspond to 2 creation and 2 annihilation operators. So that would be the third of the Cooper or the pairing channel. And well, as the name says, this has something to do with that, well, the physics should be encountered in pairs of electrons or pairs of holes. And this is actually what happens to be, the relevant for the superconductor. This is why it's called the Cooper channel. So like these pairs correspond then to Cooper pairs. Okay? But this would be diagrammatically just representing these two terms that we could have chosen. Okay? So let's just make some general statements again. So there's some apparent arbitrariness. In the Hubbard-Satonovich transformation, because as long as you're doing exact transformation, well, no one tells you how you should do it. Everything is exact, so you can do it either way. So, from a mathematical point of view, there is no difference between like different ways. However, if you think about physics, there is some correct way to do it for a given property. So there's something like a correct choice of channel in terms of physics, not in terms of mathematics. And this means that the correct choice of channel can be always only motivated by physical reasoning. Because a mathematician will look at you and say, well, it's all the same. And not by mathematics. So, as already repeated several times, the transformation, the Hubbard-Satonovich transformation, as such is exact mathematical operation, identity, no matter which channel one chooses. Okay, let me just write it. I said it several times, but maybe put to write it once. However, later at some point we want to do approximations. So later we are interested, we cannot progress anymore with exact transformations or calculations. So we're interested in low energy, something like low energy theory, which involves approximations. And this low energy theory is based on the decoupling field. So this then essentially depends on how you get the decoupling, in which channel. And there then you see, so for example, if one decouples in the channel which doesn't take into account the physics that is hidden in the problem, like if you decouple in an unphysical channel, you will have a very hard time to try to derive an effective series. It will be difficult, if not impossible, to get out of it. Still a meaningful low energy theory. And then, not only this, so sometimes you are also confronted actually not too seldom, you're confronted and also confronted with situations which require decoupling in two fields simultaneously, requiring decoupling in two fields or two channels. Okay, so this can be also the case. So as said, so if we are going to continue, we can have an example where, so this we didn't discuss, but if you look at effective theories for disordered problems, you also want to introduce some degree of freedom for which takes into account the disorder, and then, for example, you can have Cooper pairs in the presence of disorder, or like electron-electron interactions for disordered systems, and so on and so on. So there, then it can get quite complicated. Okay, so this was all about the general remarks on the Hubbard-Satonovich. So let's go back to the example of the electron-electron interactions, and then just once more also go back to the issue of the channels. So this was all very general, saying, well, you have the three different channels, and you have to choose the right one, and this is normally done by perturbation theory. We can now go back to the weakly interacting electron gas, or first at the interacting electrons, and see what these three channels are there. Okay? Hopefully this makes everything also more clear. Or questions? I mean, is it clear more or less the idea, or yeah? Did you see this before? Do you know this maybe? Does anyone work with bosonization? So there's a way to introduce bosonization via Hubbard-Satonovich transformation also. So
só uma questão. Esse canal Cooper, ele é estranho.
O que?
Esse Cooper Channel.
Certo.
Ele é um pouco estranho.
Certo.
Do ponto de vista, mas fica para long Cooper da ideia que você já tem, não tem nada de quarto Cooper, não.
Sim, sim. Esses dois estão representando Cooper pairs. Você pode ter dois eletrões que formam um Cooper pair, e você pode ter dois buracos que são a falta de um Cooper pair. Então isso é quando você tem supercondutividade, você vai ver que a gente fez lá no weakly interacting electron gas, que a gente pensou que o ground state do sistema interagente não é muito diferente do não interagente, que é equivalente em falar, vamos fazer a perturbation theory em cima do estado não interagente, que funciona, não funciona no caso dos supercondutores, porque o ground state é profundamente diferente, porque você tem Cooper pairs presente. Então, nesse caso, se você fizer o decoupling, então se você pega um gás de elétrons com interação atrativa, e você faz o decoupling no Cooper channel, você faz a teoria efetiva para esse canal e faz a mean fit analysis, você vai encontrar que você tem um mean fit que não é zero. Você tem um non-vanishing mean field, que quer dizer que seu ground state é diferente. Seu ground state tem um finite expectation value de Cooper pairs. Isso simplesmente quer dizer que seu ground state não é Fermi surface, que é o Fermi surface mais pares de Cooper. Tá? Então aí você, infelizmente a gente não vai conseguir falar sobre isso, mas a gente vai falar sobre uma coisa tecnicamente bem parecida, que é o caso do magnetismo. Tá bem?
Mas você pode trocar de canal na teoria? Digamos assim, o canal ideal daquela a mesma teoria pode ficar mudando dependendo dos parâmetros?
Pode ter regimes onde um canal tá dominante e o outro não. Isso é quando se você, o caso assim que talvez mais intuitivo é quando você tem um phase transition, tá? Aí você tem um finite order parameter. E esse order parameter é exatamente esse campo phi que a gente introduz. Então, se você tem supercondutividade, seria bom fazer o decoupling no Cooper channel, porque você vai achar que o Cooper pair tem um finite expectation value, isso vai ser o seu mean field.
Mas aí é uma transição dentro daquele canal, né?
Não, você pode ter uma transição entre canais. Você, por exemplo, se você está perto de duas transições de fase, você tem competing order, dois order parameters que podem ser, se varia um pouco o parâmetro de ordem e vai de magnetismo para supercondutividade, alguma coisa assim. Aí você tem que fazer o decoupling em dois canais e ver quando você troca um pouquinho os parâmetros. Um vai ter um expectation value finito, mean final trivial, outro não, mas se você troca um pouco os parâmetros, o outro vai ter. Então você, de certa forma, vai de...
Desculpa, a gente fazer dos dois canais.
Dos dois canais, mas...
Você pegar a teoria e fazer um, você pegar a teoria e fazer outro, fazer ao mesmo tempo nos dois, deixar...
Você faz o decoplamento simultâneo em dois canais. Isso pode ser importante quando você, por exemplo, tem vários efeitos que pode ser relevante, ou quando você está em uma região no phase space diagram, onde você está perto de uma transição entre os dois competing orders, por exemplo. Mas uma vez que você fixou, falou, eu vou só pegar esse canal, de certa forma você está preso. Você vai falar, estou olhando só esse tipo de física. Se você fala, vamos pensar que tem supercondutividade, mas tem magnetismo, não vai... Está dentro aí, porque é uma transformação exata, mas para chegar nessa física, não tem como derivar isso de uma effective theory. Você teria que fazer uma extensão de infinita ordem nas flutuações, que não é doable. Mas se pode fazer, em alguns casos, deveria fazer o decoplamento em dois canais, mas uma vez que você tem um canal, isso só... você escolheu, de certa forma, já um certo tipo de física. Okay. So let's just go back to the example of the electron-electron interaction. Okay, let's see. So now I hope I managed to do this still in time. So I now want to make actually some diagram which should explain everything nicely. So I try, I hope I manage. So let's just write down something. So let's go back to the example of electron interactions. Just once more write down the interaction term in momentum space. So S int Okay. what I did now is I just wrote down the interaction term for the electron-electron interaction problem. Okay, so what I did now is I wrote it down in a different way than we did it before. So what I did is I introduced 4 momenta, P1 to P4, and then here, this is again the 4 momentum, here we have the conservation of momentum. Okay? Now why did I introduce the 4 momentum now, how we did it before, call this P plus Q, P prime plus Q, V of Q, P prime, because when we wrote it in this way, P plus Q, P prime plus Q, we always had in mind that the Q is small while the P's are of the order of the Fermi wavelengths, no? Of the Fermi surface. So that was in a way where we always in a way chose these two to have close by momentum, and this corresponded already, like we wrote it this way because we know in a way that the density channel was important, certain kind of diagrams. Okay, so this was, when I wrote it down in the specific way, P plus Q, P prime plus Q, there was the assumption already in there that Q, I didn't ever say it, but was there, that Q is some kind of small momentum and P is large. And this was because knowing that there's certain kind of diagrams which are important, where Q then is small. So I don't want to make anymore this bias where I prefer a certain channel, but I want to now talk about all 3 channels, and to talk about all 3 channels, I should give them all like the same meaning. So the most democratic way is just to call them all by some P, and then we have to put here some momentum conservation. Okay. So diagrammatically, this is like in state P2 sigma scattering into P1 sigma, and a P4 sigma prime into P3 sigma prime, where you have overall momentum conservation, and the matrix element here, the interaction would be P1 minus P2, so it depends on the momentum exchange here. Okay, so that's the situation. Now, let's talk about the 3 possible channels that we had. So before, as said, we choose like these in a way to be one channel, okay? Where there's the same sigma, which is like this unit here. That was like the density. But now let's talk about all channels. So about pairing like these and these also. Okay? Now, what there is always the case, like how we did it before, calling this P plus Q, this P prime plus Q, P prime P. We had a summation here. Well, here's written a summation of 4 momentum, but 1 momentum conservation, so there's 3 momentum. When we wrote it in P, P prime, and Q, we already used one thing, that is, well, if you have 3 available momenta in principle, you still want the thing that we said, that these excitations here live close to the Fermi surface. Now, if you put a third, so you have 4 free momentum, you have 1 restriction due to momentum conservation, which gives you, leaves you with 3 momentum. Now you have 1 more restriction, which is not a delta function, but like a soft delta function, which says you want to have as many excitations, or you want to have actually all excitations close to the Fermi sea, and this we will now discuss will leave you always with the situation that out of the 3 free momentum that we have here in principle, you can always write them as 2 momenta which are close to the Fermi surface and 1 momentum which is much smaller than the Fermi momentum. Okay, that was one thing that we already used, but let's just try to make this. Okay, now comes like the picture. Let's see. You can see this. Where I try to explain this. Okay. So let's consider different cases. So we know already there should be 3 different cases corresponding to the 3 channels, and I will make 2 pictures for each channel. So let's make a picture here, which is for simplicity here, momentum px, py. This corresponds to p squared constant, so this would be the Fermi surface here. Okay? So let's make this 3 times. Y, px, another Fermi surface, and another Fermi surface. X and py. So this is one thing that we want to draw, and then then we want to make the analogy with this interaction vortex. So let's draw here again our interaction vortex. And 3 times. And the third time. Where here, just for later convenience, I flip here the 2 arrows. Okay, just I can flip this here. Okay? So this is now what should be the 3 channels. And then just like illustrate what is going on the Fermi surface. So this is the Fermi sea, this is all the filled electrons, but the relevant physics only takes place around here. Okay, so nothing is occupied far out here, everything is inert here, they're just occupied, they're stuck. You only have low energy available set by the temperature, so all the physics typically takes place around the temperature shell around the Fermi surface. Everything here is not interesting, everything here is not interesting, we should just talk about this thin shell around the Fermi surface, which is interesting. Now what we have here is, well, we always scatter 2 electrons, 2 states into 2 other states, so there should be 2 electrons which come from scattering somewhere, so we should draw here now 2 pairs of holes and 2 pairs of electrons. Okay? So we say here, for example, we scatter into some state P, let's say this is a state P sigma, and this was scattered from some other state, and then we have some state P prime, sigma prime, which can be anywhere else. Okay, let's say this is P prime. P prime, sigma prime. Okay, so this is just, let's say we call P1 P, then we call P3 P prime. Okay? So now what we want to have is that we want to draw 2 other states characterized by momentum and spin, and they have to be such that overall momentum is conserved. So this can be scattered from some state where now we draw like an unoccupied state of all, where it came from. This can be scattered from here or from here, but the momentum exchanged when scattering from here to here should be the same as absorbed here, okay, due to momentum conservation. And then what we want to have is that all these states are close to the Fermi surface. Okay? So we can do this in one way, which would be the direct way, which we talked about actually in the intake of electron gas. This is if the state this came from is just a state close by momentum. So assuming that P and P prime again are large, of the order of the Fermi wavelengths, and if Q is small, then this would just denote that, well, this state came from some state nearby here. Okay. So now, due to momentum conservation, this small momentum that was absorbed here had to come from this one here. So this has to lose momentum of the order of Q. And we see that, no, I did it wrong, I should put it here. Now we see that this is a perfectly possible way how to have all 4 momentum close to the Fermi surface with momentum conservation. Okay, so this was one choice where we actually choose what we choose, that the state, the electron with the spin sigma, is scattered from P plus Q into P by exchanging a small q, and the state P prime plus sigma prime came from some P prime minus Q sigma prime. Okay? So this would correspond exactly to this one here. If we draw here the same spin, so we would have here P sigma, P plus Q sigma, and here P sigma. And here we have P prime minus Q sigma prime, and this is P prime. Okay, so this would be thinking of this here being like the relevant channel. This would correspond to the density channel. Okay, so what we start out here is from a very democratic way, where we have 4 momentum, actually 3 available momentum, and we arrange now the momentum in one very specific way, because we know we always have, out of the 3 free momentum, if we want to have all states close to the Fermi momentum, 2 have to be large and 1 has to be small. This you can also convince yourself by this kind of arguments. Now we did one specific choice where we choose P2 to be close to P1 and P4 close to P3. So let me write this expression here. So this would correspond to C bar P sigma, C P plus Q sigma, E of Q, C bar P prime sigma prime, C P prime minus Q sigma prime. Okay? So this is actually the choice, having in mind that P is large, Q is small, that we always use for the weakly attacking electron gas. This corresponds to the direct channel. Direct channel, which is also called the density channel, and this is simply called density channel, well, because if you take now this as a unit, you have a sum over P, you have a sum over sigma, and this here just corresponds exactly to a density distortion by momentum Q. Okay? So the sum over P sigma here gives the rho of Q sigma, which, so this sum over P and sigma then would let us call this here rho of Q, and this is just a density distortion is Q. Okay, so that's why it's called density. Okay, so this was one choice that we could have done, but there would be also a different way, which would be, well, start again with a momentum P here, and start with, again, let's draw it something different, somehow different, and draw another state. So this would be P sigma. Let's draw the state P prime sigma prime again, which are close to the Fermi surface, so they don't have to be exactly there, but they're there. And now let's do something else. Let's, instead of saying that this state here came from this state close by, there could have been a second option where we say, well, this here came actually from a state here, P prime. And this here came from state P plus Q sigma. No, I did the sigmas wrong, sorry. This should be P prime sigma, and sigma prime. Okay, so if we draw this again here, we have an outgoing state P sigma, we have sigma, we have the state P prime sigma, incoming system P plus Q sigma prime, and here and wait, what did I do here? This is P plus Q, so this should be okay, so there's a P being scattered into P prime, and the state close by here is P prime plus Q, but this now isn't connected with this one, but with this one here. Okay? So instead of pairing these two this way, what we do is we pair these two have close by momentum. Okay? Where this is not again the same sigma. Okay? So this would correspond to pairing these with different spins. Okay, so we want to have these two close by which have different spin, and these two close by with different spins. Okay, so this is another way. Yeah, so I wanted to write down this here. Okay, hopefully one can see this. So if you so P sigma, then we have here P prime, sigma, this is P plus Q, sigma prime, P prime plus Q, sigma prime. And variables in this way. And if you write this down analytically, now what you're doing, you're not pairing these two with the same spin, but you're pairing this with this, and this with this. Okay, so to bring those close, you want to put this one over here, which is one transposition, which gives you a minus. Okay, so if you write the corresponding term analytically, you have a minus, then you have the C bar P sigma, C P plus Q sigma prime, then you have a V, which then you have a C bar P prime sigma prime, C P prime plus Q sigma prime, and C P plus Q prime sigma, and the interaction now depends on P minus P prime. Okay? That's just the second option. Again, starting out, you can choose either 1 and 2 to be closed, but now we make a different choice, 1 and 4 to be closed. Moment. Ok?
Os são menos que a altura deles
ali? Não, porque you're scattering P to P prime, P prime to P, and here just in the opposite direction, but of close by state. So the Q. So the momentum exchange is not anymore Q, but the momentum exchange is P prime minus P. In one direction, and in the other direction, P minus P prime. So this is why. Okay, so that would be the second choice. This is, I thought this would be like really explaining everything, but I don't know if this is explaining it. But it's okay. So that was the second option. Now we have a third option. So the first option, let this be close to each other. Second option, let these be close to each other. Now the third option is, well, these can be close to each other. Okay? So you have P and P3 close to each other. Or is it clear? Yeah? Okay, so this was direct exchange. Now the Cooper. Again, we want to have two close by. Yeah? So we have a P and a P prime, which are large, and a Q small. Now here we said, well, P1 and P2 are close to each other. So this would be just the density in this sense. Now we can have the opposed process like that we pair these on different, like this is scattering of a large distance, so they are close to each other with different spin, the exchange. Now if we are considering pairs, the third option of introducing two large P and P prime, but Q small now has to take into account that this is the creation of two particles. So what we can have is, we can have a state P, and we can have a state minus P. So if this is two electrons, if these two electrons scatter into two holes, P prime and minus P prime, yeah?
Quando você desenhou anteriormente o canal Exchange, estava como se fosse X.
Sim.
Agora você está fazendo...
Só porque eu troquei, eu tenho certa liberdade como desenhar, né? O que eu fiz antigamente, eu desenhei dessa forma. Se você faz dessa forma, virar assim. E por isso você tem o X. Agora eu desenhei assim, que no mesmo lado tem um outgoing e um incoming. Certo? Então você tem essa liberdade, tá? Agora, a terceira opção é correspondente a esse canal, que você tem dois incoming e two outgoing, and the incoming and outgoing are paired, but to make it convenient, I flip now here again. Okay, so this would be the Cooper channel. Okay. So what this means again, if you take two momentums which are opposite on the Fermi surface, yeah, they can sketch into any other two opposite. If this is P and this is minus P plus some small mismatch Q, yeah, and this is like P prime in here minus P prime and minus Q. Okay, so this is another way how you can achieve that you have out of the three momentum too close to the Fermi surface, which is now P and P prime. But now you shouldn't say think of P plus Q, because P plus Q works for the density or exchange, but you should think of minus P plus Q. And this just reflects the fact that you do not talk about pairs or channel formed from an electron and hole, but from two electrons. Okay? You always want to form objects with a small center momentum, center of mass momentum. I should have probably said this the right way. Like density here, electron and hole, these two, P and P plus Q, because one is an electron, one is a hole, have like absolutely small momentum Q. Okay, so the same here, the P and the P plus Q, electron and hole, they have a center of mass, let's say momentum small q. Now if you want to do the same for two electrons and two holes, you shouldn't pair P and P plus Q, but P and minus P plus Q. Okay, this is some object that is formed with a small center of mass momentum, and this here also. Okay? I mean, just go through this once yourself. Okay, let me just finish this. I tried my best, but I think it's just one should be able to explain it better. I have to think how to explain it better, like for the next time. But let me just draw this once down. So you want to pair these again with a small momentum mismatch. So sigma prime, now with a minus P, and here you have a P prime sigma, and P prime minus P prime plus Q sigma prime. Okay? So again, you form here an object which has a center momentum. This plus this is Q is small. Here you have an object. This minus is a momentum because one is created, one destructed. This Q is a small momentum. Here again, one is created, one is destructed. This momentum minus this momentum is a small momentum Q. Okay? So this is actually a good exercise. Let me just write down here once what you get. So what you want to pair is an electron P sigma with an electron minus P plus Q sigma prime. Now we have an interaction which again measures the difference in momentum. And you have like the whole P prime sigma prime and minus P prime plus Q sigma. Okay, so this again. So it's a good exercise to think once. You start out from this interaction, you have three free momenta. You can draw them how you want, but you have the restriction that all the four should be on the Fermi surface. You have momentum conservation, you have three free momenta, and the only way is to have two like arbitrary and then a small exchange. And this small exchange means that a state can just scatter to a closed one, like this way, or a state can scatter like over large range momentum, but then the other has to scatter in the other way. So then you arrive again at a pair of an electron and hole which are close by in space, but they have now different spin. And if you look at it, if you pair them, you you get a minus, so that's the exchange process. And that there's a third way where actually you pair an electron and a hole. So here you would have the scattering, so where you pair two electrons and two holes, so you want to scatter again from some arbitrary, let's say here p prime to a minus p plus q, and then you have to have a process where you scatter from, when this is p prime, from a state on the opposite side of the Fermi surface, so minus p prime in some vicinity, into a state of the vicinity of minus, of this minus p, so in the vicinity of p, okay? So then you can pair these here to form an object with some center of mass momentum q, which is small. Okay, this is the three ways you can do it. Okay, and all this is guided by the idea that you already talked about before. So you want to have excitations close to the Fermi sea, and now you see that this object that you introduce here, which will correspond to this here, will have a sum over p, which is over the Fermi surface, a large sum. This object here will have sum over p, which is over the Fermi surface, and this here also has a sum over p, which is Fermi surface. And this depends all on the small momentum q. And it corresponds to saying, well, you think of this, it's a pair, it can be anywhere, yeah, because momentum conservation only says that the q here has to be the same as here, but the p and p primes are unrelated. In the same way here, the p and p plus q can be paired, but can be anywhere, this can be anywhere, because you guarantee that this comes from a state that is similar to that which the scatters in. So this is also very increased momentum conservation. P and p prime can be anywhere in momentum space. And here it's the same, you pair these two, and this p and this p prime can be completely unrelated, because you only guarantee that, well, here you change in total your momentum by some q, because it's two electrons and two holes, and this is on this here. Again, we have two free summations of the terms. Okay? So that is for the weakly interacting electron gas, three different ways how you can introduce some degree of freedom composed of two electrons, in which you know now already depends only on small momentum q. Okay? So the p is large, is the momentum of the electrons, high energy scale. We want to derive a low effective theory, where the fluctuating field only is like a softly varying, spatially varying field. So the typical momentum, the typical length scale, which the scales is very large, so the momentum is much smaller than this microscopic energy. So when we introduce these channels, we make already a separation of energies. So there's a large energy, which is the Fermi surface, but we want to have a theory which doesn't live on energy scales of the Fermi surface, but on the temperature. Okay? And this is a scale like the Q depends on, because this Q has to do with the broadening of the Fermi surface. If you don't have any broadening, like due to temperature, whatever, there's little phase space. So this is proportional to the likely broadening. Okay? So I think like the only way to understand this better, everyone has to sit down himself and just go through this. And if there's a question, please ask me again. I tried my best. Okay.